Now, which one of these problems here needs to be rewritten? It's not in the right form at the moment. Number one, the last one, right? If to rewrite this as what? Yeah, so just remember, radicals are, to be honest, when I teach this, I say, I wish to God we never came up with radical notation. It is stupid. If we just knew this, and some of you guys are like, no, it's 4 to 4, no, it is. Well, you wouldn't know what 4 to the 1/2 power is if we taught it like that from the beginning. This notation sucks. You almost always have to rewrite it like this to do something. I'll let go. So go back here. What's the derivative here? Nice. Start off nice. What about this guy? Yeah, negative 33 x to the 10. This guy. 9x squared plus 2. I like it. And look real quick, you see how that's a line, the slope of that line is 2, so that 2 represents this whole thing. I mean that's, or the constant goes to 0, either way you look at it. And then this guy, he's written correctly. Gas. So that's a really easy thing to miss up on. If it's already negative, it's going to get more negative. For some reason, people go the other way. No. This guy is written the right way. Two-thirds x to the negative 1/3. I love it. The gas. Bless you. Real quick question. Bless you.
Thank you.
Where is this guy not differentiable? Where's that function not differentiable? Look at the derivative. Where does it not work? No, it's okay there. What's on the bottom of this? X to the 1/3, right? So what can't you have on the bottom? 0. So this is not differentiable at 0. When you now, that means the derivative does not exist there. Which means one of several things. One of which is it's infinite there. If you graph x to the 2/3, you end up with something like this. If you graph it, it's actually x to the 1/3 squared. So it ends up being like this. Point. So what happens right there, derivative-wise? That is a cusp. That's one of those not differentiable places. So when you take the derivative, you can tell really easily where it's not differentiable. Where's the derivative not defined? Okay. Did that have anything to do with the problem I gave you? No, it's just a little extra. Then this guy is easy now, then I got it written like that. 2 seconds away. 9 minus 7, 2. Sweet. What's up? What's 9 sevens minus 1? Yeah. And again, it's too beautiful to believe. The reason you can just do 9 minus 7 is because that's what's going to happen if you make LCD, 9 minus 7. So the shortcut is just do the top minus the bottom, and that's what it becomes. Or just do minus 1, make LCD, whatever, it's going to work. Okay, I like it. What about this dude? So that's the one I just talked a little bit about. You're going to see this question over and over through the whole semester, because it is a huge part of this. What's wrong with this, though, this function? Yeah. So rewrite the function. I like it. And it's not just because I'm picky as hell on notation, but do not take the derivative of part of it, rewrite the other one, and then catch up. No, rewrite the function and then take a derivative. Because otherwise you're going to forget when the hell you took what, and you're going to do a derivative twice or something crazy. So what's that prime going to be?
12x to the 3rd plus 2
I'm with you.
I forgot that. No, it's like, yeah, that one was.
Thank you. Why are we doing this, by the way? Why are we taking a derivative here? Not just because it's on a derivative worksheet, but yeah, I need to find the slope. To get the tangent line, I have to find the slope, and in calculus, the slope is derivative. So what do I plug into the slope function to get this? 2. What's this 47, of course? That's the output to this, right? So if I plug a 2 in, I end up with, whoops, sorry, here. 12 times 2 cubed plus 2 over 2 squared. Who is it?
96.
Yeah, I like it. 96.5 FM. And what do I do with that? What's that? Yeah, that's M. So you got,
Y minus 47.
I like it.
96.5 minus X.
Gas.
Y.
So y equals 96.5x twice 96.5 is 193 plus 47. 96.5x minus 146. Now, tangent lines in general are important to calculate because they tell you the trajectory of something at that moment. I've got a missile coming, I want to be able to figure out the tangent lines at certain points. So I can figure out where the hell this thing is going. Horizontal tangent lines are kind of especially useful for certain things. For example, if my profit function looks like this, where do I want to be? And what's special about that point? The tangent line has a slope of 0. I like it. We've talked about that kind of thing. There was like a profit, I can't remember what it was, revenue function we looked at before. So if I'm up here, I am at the optimal for now. It also occurs here, doesn't it? Right? So you want to find all the places. And it also occurs where else? At some sucky places, right? So we are going to get to the point where we're able to use tests to figure out, is it a hill or is it a valley? Right? If it's a cost function, I want to be there. If it's a profit function, I want to be there. I like it. So here, how do I get that horizontal tangent line? What does that mean, horizontal tangent line? The slope is 0. So I find the slope first. This is nice. Then I take that and set it equal to 0. Anyone notice that you can divide by 3, make it a lot easier on yourself. And how do you factor that? If you left the 3 in there, it'll still work. But my God. Yeah. Which is positive. 7. So at x equal to -7 and 3. And the question asks, yeah, so x answers are where things happen. Y answers are what happens there. So find all places where the tangent line would be horizontal. It's at x equal -7 and x equal 3. Is it a max or a min? Well, we still have to figure out ways to determine that. All right. How do you feel about that so far? Awesome. Okay. Now, so we only have one rule. It already basically takes care of anything polynomial. So we've destroyed a whole class of functions. We were like, if you're this, we got your number. You can get a derivative. Kind of the next level up from straight up polynomials, like rational functions. So there's two rules we're about to talk about. To kind of build on top of what we've done so far. They are the quotient rule, which is what a ratio of polynomials is a quotient. Right? So if I have a rational function, if I know a quotient rule, what to do if I have a function divided by another function. But before we talk about that one, we want to take a step back and talk about a slightly easier one, and that would be the product rule. Okay, so this is exactly like I told you. We're going to talk about classes of functions. Is there a general rule for that class? If I have a powers, if I have polynomials, we got a general rule. Then I want to connect those with overarching rules. These are not rules for types of functions. These are just general. If I have a function divided by a function, this is going to work. If I have a function times another function, this is going to work. So I'm going to prove this one, and then I'm going to talk about this one. So the product rule, of course, works for it. So anytime we want to prove a rule involving derivatives, we have to go back to the definition of derivative. It's a limit process. So we use that process to prove things now. So I want to look at this. So this is what I want to look at. And so I need to limit as h goes to 0 of f of x plus h, g of x plus h, minus f of x, g of x, all over bless you, h. Now again, do you ever have to do this yourself? If I ask you in the bonus question, rederive the product rule, yeah. I'm not going to make you do this by yourself, because especially not this one. What we're about to do happens a lot in proofs. The first few times you see it is like, what the shit? Where'd that come from? But I want to, the motivation for what they did with this is, do you see parts of f prime in here? What would f prime look like? What's f prime of x in limit definition? I see that shit. I can't pull it out. Some of you guys seem to think you can, but I can't just take these parts and put them, there's a, no. But my motivation is I see the parts. Do you see G prime? Yes. So there must be something I can do maybe. I'm going to introduce a term. So I'm going to add a term to the top, which means I'm also going to have to subtract it. So I always go back to Indiana Jones. Remember completing the square? Oh my God. Do you remember completing the square? You're all like, what did it have to do with Indiana Jones? I'm sorry. Real quick. Side note. So if I had this, and I wanted to put it in standard form, do you guys remember this kind of problem? What kind of thing is that? What kind of function is that? If I graph it, it's a parabola. I like it. So I want to put it in a form where I can see the most important parts, which is the vertex, for one thing, right? So I want to complete this guy square. Does anybody remember how completing the square works? This is applicable, by the way. If you come up this semester.
It's using a null line, essentially.
See it?
Using like a null line. That's what it's called. The Greek way they would do it is add a square and they would just add.
Oh, yeah. So that's the beautiful geometric interpretation of what we're doing. We are actually completing a square, which is neat. But I'm just talking algebraically.
Yeah,
I love it.
It's multiplications of terms and
So
you get two rectangles.
the nuts and bolts of it. Beautiful. So you take half of the middle dude and then square. Why do you do that? Because that's what works. Whenever you have something squared like this, that's where it comes from. That's what it leads to. Right? So if I take half the middle term, that's 2, square it, that's 4. This is what I have to add. Well, if I add 4, I better do what at the same time? So that's the whole Indiana Jones, which of course everybody's seen that movie. It's from the 80s when they made really good movies. You take the gold idol off and you put the sack of sand there, and unfortunately he didn't balance his equation correctly. It's a freaking boulder came down and almost killed him. But if you put something there, you better take it away at the same time to keep everything the same. He was off a few grains. But here we get x plus 2. See, that one tells you how the hell to factor that shit. All right, so what's it got to do with what I'm going to do here? We're going to do the same kind of thing, believe it or not. We're not going to complete the square. But I am going to add and subtract something here to try to pull that and the G prime shit apart. Okay. I'm sure you guys got what you want from that. Let me rewrite this here. All right, so we got this part. It'll leave some room here. Well, let's see. Just right. Okay, here's what I'm going to add to this. What's going to work well? Pink. Whoa. All right. Totally good for high. Oh, let me put this at the end. Keep this so straight. So I just rewrote that there with some room in the middle. So now I'm going to subtract f of x, g of x plus h, and I'm going to add f of x, g of x plus h. Now I could have subtracted 11 and added 11. I could have subtracted w of x and added w of x, because then I would have done nothing. So you're all like, good job, Jeff, you did nothing. So this feels really strange, possibly, to some of you guys. Right? You're like, I don't know. But again, I made it look different. Now I can collect things in a certain way, just like we collected things here. So looking at this piece of it, all right, this H is over here. What do I get here? Keeping with the pink here. Like, what can factor out of this piece? G of x plus h. I like it. What do you have left? If anybody's concerned why that is not also over h, I only have one h down there. There it is. If there was another h, that's only h squared. I've got h squared. Just in case somebody's like, what? Okay. Plus, what can I take out here? What comes out of these two? F of x. And what's left? So the motivation was, I saw parts of f prime and g prime in there. There must be some way to tear that shit apart. Because I know how to do f prime. I know how to do g prime. I just don't know how to do f times g. I don't know how to get that prime. Right? So what happens as h goes to 0? What does this become? Don't overthink it. This piece by itself. H goes to 0. This is g of x. And of course, this is the definition of f prime plus. That's f. I don't give a shit what h does, right? The h goes to I don't care. But this piece is g prime. So let me rewrite this a little bit better. A product of functions, I needed to take its derivative. I love the idea that's set up here because it continues throughout all of calculus. This idea of, see how each function gets its own term. Derivative of f times g, now it's g's turn. So they each get a turn. So let me give you a very basic example of why the derivative of this can't be simpler than this. So let me write x cubed in a weird-ass way. Now, if somebody thought that the derivative of the product of two things is just take the derivative of each of them and multiply it. Right? So somebody always believes f times g prime equals f prime g prime. So wrong. But let's see what happens. If I do think that, what do I get? What's the derivative of x? Let me do it like this. What's the derivative of x? 1. What's the derivative of x squared? 2x. Is the derivative of x cubed equal to 2x? Alright, this is shit then. Right? So the derivative of a product cannot just be the product of the derivatives. It can't. Why? I just need one counterexample. Throw that shit out. Now, what I'm about to do is not a proof. This is the proof, but this is a concrete example of that proof. What's the correct way to do this? So f prime of x. Here's the rule. And let me say this. So I know quite a few of you taken calculus before. Whatever your teacher told you, fantastic. If you write the rule and then do the derivatives, your life will be so much easier. Because that is two different things. So many people try. Now, this is a really basic function, right? Basic function. It's not going to be hard to keep track. But what do I mean by that? Well, what's the rule say? This guy gets a turn times this guy, plus this guy stays the same, and then it's this guy's turn, right? Is that cool? That's writing the rule, and then you worry about doing the derivatives. You don't do it all at the same time. Calculus is hard enough already. Why make it even harder? So what's x prime? Derivative of x. 1. X times, what's the derivative of x squared? So I get x squared plus 2x squared is? And is that the right derivative? Yes. All right. So believing that the derivative of a product is just derivative of each times each other is obviously wrong. That's the proof of what you do. Here's a beautiful example of why it's got to be this way. Oh yeah, a decent example. Okay. Call me on shit. Beautiful. All right, so let's try something a little more interesting. Let's see. Now, let me say this. Until we learn something called chain rule, the product rule is going to be pretty lame. Meaning, what could I do with this before I took a derivative? Could I just combine them? I like it. You with me? All right. Chain rule is going to allow me to look at stuff like 4x plus 7 to the 8th power times square root of x minus 2 to the 11th power. Do you want to simplify this? Meaning, multiply 8 of these by 11 of those. Oh, yeah. If you do, it'll work. I don't want to do that shit. I don't want to do it. Do you want to? I'm not going to look at that, to be honest. I'm like, okay, that's fine. We can't do this stuff yet. Because I don't know how to do, what does this look like? This is a function inside of a power. I don't know how to do that yet. That's another rule we're going to have to learn. It's called the chain rule, and you'll see why when we get there, why it's called the chain rule. There's a reason. Okay, but right now, you're just going to have to deal with lame shit. The book's going to say use the product rule, and you're going to have to do it. Right? The nice thing is I could simplify this and check. Same way we did that problem over here. But if I do use the product rule, how's that? You guys try to do that. Try to write it out. Use the product rule.
It'll tell me how much